So we're continuing to think about a sample. So IID, independent and identically distributed random variables, capital N of them. So N here is the number of observations in our sample. And they are, because they're a sample, that means that they are independent and identically distributed. And part of what that means, the identically distributed part, means that they have the same expected value and the same variance. Okay? So each of these x's is a realization of a random process that is the same for all the x's. Okay, so you can think about each x as the outcome of an individual experiment that's all being governed by the same PMF or PDF here. And we're going to often, because they have the same expected value and the same variance, we can use symbols for them. So I'm going to let mu be the unknown expected value of the all of these x's. So I'm not saying any individual x necessarily has the expected value, but that is their that is the expectation of the process that generates them. And the process, they all have the same variance, sigma squared. Okay, that's our sample. And as we said in the last video, a real natural statistic to calculate. So one of these like G formulas that we could apply to a data set. So we're applying it to all the x's, to the vector x1, x2, xn here, is an example of that is mn. Mn is going to be the sample mean, and I'm defining that as this formula. Take those x's, add them up, and divide by n. So that is my statistic. Yes, it's a formula that I apply to my data x, but it's also a random variable. So what I can do, and what I am going to do right now, is I'm going to take the expected value of the sample mean. Okay, so we're treating this statistic as a random variable, and I'm going to find out some things about its distribution. And because the statistic is a function of the data, its distribution and its moments are going to be derived from the process that generates all the x's. That's going to, another phrase that maybe is worth noting here is that the x's have the same data generating process. Okay, so that the sample means distribution derives from the distribution of the data here. So this is the kind of problem we've been doing all quarter. We want to know the expectation of m, which is this function of these random variables. We can apply what we know about the algebra of expectations here. So let's do that. So we're just taking the expectation of random variable x1 plus random variable x2 all the way up to random variable xn, dividing all those things by n. N is a number. We know how many observations are in our sample. And so let's see. So this is the sum of a bunch of random variables. So first thing we could do is we could say this is the sum of x1 over n plus x2. This lost an expectation here. It's the expectation of x2 over n. Again, we can apply the expectation to every element. It's an n over n. So that's a rule that we derived kind of midway through the quarter, that the expectation of the sum of two random variables is the sum of the expectations. That's just exactly what we've done here. Also, what we have here is a random variable multiplied by a constant by 1 over n. So this is our kind of standard. The expectation of a linear combination is the linear combination's expectation. The expectation of ax plus b is a times the expectation of x plus b. So b equals 0 in this case, and a is 1 over n. So we can pull out those 1 over n's. Let's do that. So it's 1 over n ex1 plus 1 over n ex2 all the way up to 1 over n exn. Okay, fine. I'm going to factor out that 1 over n, but you know what else I can do? I can use the fact that these x's are all identically distributed. The expectation of x1, I know what that is, it's mu. The expectation of x2, it's mu. Xn, it's mu. And maybe I shouldn't say I know what it is, because I don't know what it is in terms of a number, but I know that this expectation is the same as that expectation, is the same as this expectation, that all those x's have the same expectation, because that's what it means to be identically distributed. Okay, so look what I'm doing here. I'm factoring out this 1 over n, and I'm replacing this expectation with mu, and the next one, and all the way up to xn. How many terms do I have in this sum? Well, I have one for every element in my sample. There's n of them. So I have 1 over n times mu. The expected value of the sample mean is the population mean. That's what I just showed you. Okay, so we have this data set, we have this set of observations, X, they're IID. We take we feed them into this formula to calculate a single number that summarizes all the X's here, and the expected value of that number is the mean of the process that generated all of them. This actually ends up being extremely cool. What this says is that the sample average, the way we defined it right here, this simple average of the x's here is an unbiased estimator of the population mean mu. It's an unbiased estimator of the expected value of this process that is generating all the x's. So we can't observe mu directly, but we can estimate it in an unbiased way by calculating the average of the x's. This is what we do over and over again with statistics. We have something that's of theoretical interest to us that we can't observe directly, but we calculate data that's related to it. And ideally, or we find data that's related to it. And ideally, we calculate statistics that give us unbiased estimates of the things that we can't directly see, but that we care about. And the unbiasedness means that we're not systematically saying that mu is higher than it is. We're not saying that it's systematically lower than it is, that on average, over the long run, the sample mean in expectation gives us the population mean. Okay? The in-expectation is necessary because the sample mean, there's always going to be randomness. That's the world that we live in. That's the world that causes us to want to understand things through statistics. But the way we do it is through these ways of processing the numbers, processing the things we can count, the things we can observe in a way that gives us an estimate of the thing that we care about that again is not systematically too high, not systematically too low. That is the best that we can do. Okay. All right. So one really important takeaway from this lesson going forward into 200B, something I really want you to remember, is this fact that the sample mean is an unbiased estimator of the population mean. Another thing that I want you to kind of take away is this idea of what it means to be an unbiased estimator. So let's just kind of say in general what we're talking about here. In general, statistic g of x, okay? In general, this formula that we apply to our set of observations is an unbiased estimator of unknown quantity gamma if the expectation of the statistic is gamma. So this kind of derivation that we just did on the previous screen, showing that the expectation of mn by filling in the particular formula, it's the particular g that we're interested in, and showing that its expected value is the parameter of the distribution that we care about, you're going to be doing a lot of that going forward. So one of the reasons why in this class we did a lot of those derivations involving expected values of complicated things is because that's how we figure out whether our statistics are biased or not. And we really want our statistics to be unbiased. We really want our estimators to not be systematically wrong either in a too high or a too low direction. So just again, going forward, the x's are what we observe. GDP in a bunch of countries, when and where wars occur, responses on surveys, voting outcomes. These are real things that we go out in the real world and estimate, or we go out in the real world, sorry, I did not have said estimate, we go out in the real world and we observe them directly. And we do that because there's something of theoretical interest that we're trying to figure out. Do countries that trade with each other, are they less likely to go to war with each other? Is voting behavior driven by identity or political beliefs? These kinds of questions involve these theoretical concepts that we can think about, but that we can never really measure directly, and those are our gammas here. Okay, so these are what we care about. These are our concepts that come from our theories about how politics works. And the G's, these are the statistics we calculate. Okay. So your substantive classes, whether you're in political science or any other field, they are going to be leading you to figure out, what are the gammas that we're interested in, what kind of data could give us some insight into these quantities of interest. Are going to be different for every field, but the statistics, and the reason why we can kind of all study statistics together, the way we take our samples and apply formulas to them to get numbers that are relevant for our theory, that's what we're learning in methods classes going forward. And one of the things that we want our statistics to always have, we want the estimates to be unbiased estimators of the thing that they're meant to represent. Okay, so we'll see more of that in the coming lessons.